Okay, so this problem, the fourth problem of our sample, actually it is the sample one of our final. It is actually asking us to determine the second moment of area or the inertia, and the radius of gyration of the shaded area about x-axis. Okay, so actually again it is examining our uh it is examining our concept of a second moment of area and the radius with duration. So and first is first the question is here is that what formula are we going to use here? It is actually it, it is actually defined here, right? So if we go to the appendix, we're going to have the second moment of the area. It is actually at here, area moment inertia, right? So basically, it is in integration of the square of the integration of the square of the coordinate here, right? Okay, so uh, now we're going to apply it. Okay, so first, if we're going to solve for x, it equals to what? Okay, so it equals to the integration of area of y squared, right? dA. And and okay, so actually for xi it is y squared. For iy it is x squared. Why? It is because we actually y is actually the distance from an arbitrary point in the area to the x-axis, which is typically the y coordinate of the arbitrary area. It is the reason why for x we have y here. Well, for the integration of an area, and typically how are we going to approach that? Okay, so for for Cartesian coordinate system here, typically what we do is to divide, right? What we do is to divide here, and here naturally we were going to first divide along x, right? So we are going to first divide along x, and divide the we are going to divide the area into several infinitesimal areas, right? Or a slice. Okay. So, and for a specific slice, okay, for a specific slice, typically it is the location is described by x coordinate, and we are going to further divide it along y direction, and then it will going to be divided into infinitesimal area, right? So the width is actually the dx, and for a specific area, if I take that out, okay, so the width is actually dx and head is actually dy, right? Okay, this kind of dividing along y direction is applied for every single infinitesimal uh uh, uh infinitesimal slice along y. Okay, so now okay, after we divided that, we can go ahead to take a actually take the summation in continuous case that is actually integration, right? Okay, so now first if we have the first divided, and we're gonna have we are going to have that as the outer integration, right? It will be we first divide it along x, and we're going to have integration on x, and from where? Okay, so it is from A, right? It is from A to B, right? Okay, then we have integration of from where? And for a specific x, right? For a specific slice of x, it is the integration from y equals to 0, right? From y equals to 0 to where? To the actually to the curve, right? And the curve at the curve here, y equals to c divided by x, right? The curve here is y equals to c divided by x and c equals to 6. And then it is integrate. We are integrating what? So actually, it is integrating y squared here. Okay, so now it becomes a so now it becomes a double integration. And to approach the double integration, we're going to integrating the we are going to integrating the integrate inside, right? We are going to integrating the integration inside and then integration outside, right? So the integration inside will be so it is integrating integrating of a polynomial here, right? So it's gonna be okay. So actually, gonna be uh so y square. So it is y to the power 3 divided by 3, right? And then lower bound 0, upper bound 6 divided by x, and then dx. So it will equals to integrating from a to b, and then it is actually 1 divided by 3, and then to the power of 3 here, right? Okay, dx, right? So now, okay, so actually the problem statement didn't show us a and b. Actually, the a here equals to 1 and b here equals to 3. Okay, so now we're going to integrating from 1 to 3. And please note here, actually we were supposed to have the value of a and b here. It is actually the type. Okay, so and we're going to have it actually becomes 1 divided by 3 to the power of 3, and actually it is x 3 here, and the integration of x. Okay, so if you are integrating that, and you are going to have so it's gonna be -2 and x -2, right? X to the power of the -2 here. So it's gonna be so we have lower bound and upper bound, and you can try to evaluate it. Okay, so it actually equals to 32, right? Okay, it actually equals to 32 here. Okay. Okay, so given that we have 32 here, we are going to go ahead and move on to the second. Actually, the second thing that it is asking is actually the radius of a duration of the shaded area, right? So it is kx, and we know that kx is actually equals to ix divided by area and the square root of that. And we already know the x here, but we are supposed to find a area, right? So we're gonna have we're gonna first solve for the area, and area equals to, so it is a integration of area, right? So area is the summation of each infinitesimal area. So we see that it is a equivalent. So it will be pretty similar to the integration of ix, but in the integration to find out ix, but it is actually have everything but the y square here, it will be directly dy and dx. So we first have the integration inside to be, it is actually upper bound minus lower bound here, right? Okay, so then we have an integration of 1 over x, it is 6 over x actually. So it will be 6 times ln of x. Okay, so if you evaluate that, it will be 6 times ln of 3. Okay, 6 times ln of 3 minus ln 1. It is actually 6.59. Okay. Okay, so now we can go ahead to substitute the values here. The kx equals to x divided by area square of that, and ix equals to 32, right? Area is actually 6.59. Square root of that, you're going to have that equals to 32 divided by, okay, the area square root, which is 2.2, right? Okay, so it is answer here. Okay, so now actually this question is actually examining our concept and understanding of second moment area, inertia, and the radius of radius of deterioration here. So so you see that here we use the integration of area a lot of times. So of course there's two key things here. One thing is that what formula are we going to use here? And of course, so although we give all the formulas in our appendix, it can be helpful if we understand the meaning behind the formula. And the second thing is that after we know the formula that we're going to use, how are we going to perform the integration? Although it is not belonging to in this class, it's the basic skill that we're going to use to solve that. It is pretty important to ensure that you are familiar with it. Okay.